Hello, I'm Oliver. In this video, I will tell you about different ways to advance time in your agent-based model. To begin with, let's look at a simple agent-based model. So the basic unit of your agent-based model will be agents, and the agents are supposed to do things. So initially, your implementation might look something like this, where you have an agent and they're supposed to do one thing, and then they do the next thing, and so on. And usually you will have more than one agent, so you will have a loop that goes through all agents, and all agents do this thing. And then usually the agents aren't supposed to only act once, but multiple times, so you might add in a second loop that repeats this for a number of times. And then you might not want to have every agent execute every action in every step. So the result could look something like this, where each agent only acts with some probability for each action. This is what we call a discrete time simulation. And many agent-based models are designed this way. If you imagine how time advances, we see we start at some time point 0. This is where the step counter is 0. Then all agents act simultaneously at this time. Then we advance time by some delta t. This is the step size. And then all agents act again. We advance time. All agents act. We advance time, and so on. This way to advance time can lead to some problems. Let's have a look at this example where we have a grid and the agents want to move around on the grid, and every grid cell may only be occupied by a single agent. So what happens in a situation like this, where there are two agents who want to move to the same cell X at the same time? So in reality, one of them would move first probably, but in our model, there's no first because there's only this time step and everyone acts simultaneously. The same problem can also occur with different actions, potentially of the same agent. So imagine a model of infectious disease where your loop might be set up in a way that you either always process the infection first or the recovery first. And you might imagine that this has the potential to lead to some bias in your results. So what's the source of this problem? Well, most real-world events actually do not happen in fixed intervals. So the actual events you want to simulate would usually happen between these time steps. So these are these red tick marks. And sometimes we'll have only one event between two time steps. And sometimes there will be multiple events, and they all have to be processed simultaneously at this following time step. This highlights another problem, another potential problem with this kind of implementation, and that is that you introduce an approximation error in your event timing. That's especially important if you then want to analyze the time between events. So what can we do about this? One thing we might want to do is to reduce the size of the time step. That might look like something like this, where I've just reduced the size of the time step by a factor of 4. How do we do this? Well, usually what we have to do is we have to reduce the probability with which the agent acts in each step appropriately. This improves the problem, because now most of the time there will only be one event in each step, so there's no order of events issue. And of course, if our time step is smaller, it will be closer to the events, and our approximation error will also be reduced. but both issues improve, but they don't go away. And also very important, this will increase the runtime of your simulation, because now you will have to check very often if the event should actually happen, and then you will have then most of the time it won't. And you have many time steps like these and this and this and these, where there will be no events at all. So can we do better than that? And the answer is yes, we can. What we can do is get rid of the time step completely. So we, instead of advancing in steps, we advance directly to the precise time of the next event, and then to the next event and the next event, and so on. Here we view time as continuous and not as discrete as in the above case. This type of simulation is called a discrete event simulation. And in the rest of this video, we will look at one example of how we can implement such a discrete event simulation. If you want to have a closer look, I would recommend you the book Simulation, Modeling and Analysis by Avril Law, especially the 5th edition, which includes a chapter on agent-based simulation specifically. As an example, we'll look at a simple SI model of infectious disease. In an SI model, persons are either susceptible to the disease or already infectious. And in our version of the model, the agents form a network, and the disease may only spread through this network. So this on the right is our model state that we will use for the example. We have 4 agents, and A and B are initially infectious, and C and D are initially susceptible. We will use an implementation of this model in the modeling language ML3, which is a modeling language that is specifically designed to implement agent-based discrete event models. We will not have a detailed look at the language, but if you're interested, I would recommend you to this publication. So in our model, we have 2 actions that each agent can undertake, or 2 events that can happen to each agent. They can be infected or they can recover. And in ML3, each of these events is implemented as a stochastic rule. So in this first rule says that every agent who is currently susceptible will become infectious with a certain stochastic rate, and this rate is 8 times the number of infectious neighbors this agent has. And the second rule governs the recovery. So an agent who is infectious will, with a constant rate b, will recover and become susceptible again. Each of these rules describes the Poisson process, where the time between events is governed by exponential distributions, and the rates of these rules will be interpreted as the parameters of these exponential distributions. We'll see that through the next slides. So to execute these events, the first thing we have to do is to schedule all the different events that could happen. And we will start with the infection events and then go on with the recovery events. So down here we have our timeline, and currently we're in this state, so it's the state above, and we call it S0. So now we go through the agents and look what happens. So the agent A is already infectious, so they can't become infected. The same is true for B. C, however, is susceptible. And that means we'll now calculate the value of this rate, and the value, we'll call the value of this rate lambda. And it's A times 1 because C has one infectious neighbor. We'll then draw a waiting time delta t from an exponential distribution parameterized with this lambda. And this waiting time is then added to our current time to get the time where this event is scheduled to happen. So now we do the same thing with D. D is also susceptible. We calculate lambda, we draw from the exponential distribution, and we get some time where the event is scheduled to happen. So in this case, even though the rate for D is higher, because D has 2 and not only 1 infectious neighbor, the infection event for D is scheduled later than the infection for C, because this is a stochastic process, so this can happen. And then we continue with the recovery events. So we have a look at A. A recovers with some rate B. So again, we draw from the exponential distribution and I get time. And then B, the same thing. And C and D are not infectious, so they don't need to recover. Now that we've scheduled all events, we can go on to execute the first event. What we do is we always execute the event that is scheduled to happen first. And in this case, it's the recovery of the agent A. And when we execute it, we get this new model state where everything is the same except that the agent A is now susceptible instead of infectious. And if we have a look at the timeline, it looks like this, that previously we were at this time in state S0, and now we are at that time in state S1. And these are the events we still have scheduled. One might think that the way to proceed would be just now to execute the next events, but that would be a mistake, because if we look at C, they can now no longer get infected. And if we had look at D, their infection rate will have changed because they have one fewer infectious neighbors. So what we have to do is we have to carefully consider if we have to reschedule any of these events. And this is what we do next. So for rescheduling, we have to basically keep in mind every event that might be affected and change its scheduling. So let's again start with the infection events. We begin here with just making a copy of our current timeline to keep track of the changes we're doing. So first we look at the agent A, and A is now susceptible and they have an infectious neighbor, so their infection rate is 1. So we draw from the exponential distribution and we get a time for this infection event, and it's this one. We look at B. B can still not be infected because they're already infectious. C has no longer any infectious neighbors, so this rate is 0. And if the rate is 0, it means the event can never happen. So we remove that. And then we look at D. And for D, previously the infection rate was 2 times this constant A, because they had 2 infectious neighbors. And now the infection rate is only 1 times A, because there's only 1 A neighbor. So we have to reschedule the event. And in this case, we do that by just repeating the scheduling procedure, drawing from the exponential distribution and so on. And we end up with this new time of infection for D. Keep in mind that this rescheduling by just repeating what we did before is only possible because we deal with exponential distributions, and the exponential distribution is memoryless. So we don't care about how long So how long in the time before this event might have already happened or something like this. If we had different distributions, we might want to take such things into account. So let's continue with the rescheduling of potential recovery events. And again, we look at A can't recover, so there's nothing. The recovery rate for B hasn't changed because it's just this constant B, and C won't recover and D won't recover either. So nothing to do here. And now that we've rescheduled everything that needs to be rescheduled, we can choose the next event and execute it and so on. In this case, unluckily for A, they will get infected again right away. So let's continue with the rescheduling of potential recovery events. And again, we look at A can't recover, so there's nothing. The recovery rate for B hasn't changed because it's just this constant B, and C won't recover and D won't recover either. So nothing to do here. And now that we've rescheduled everything that needs to be rescheduled, we can choose the next event and execute it and so on. In this case, unluckily for A, they will get infected again right away. Let us now look at the simulation algorithm as a whole. So we have one variable S, where S is our current state, and T is our current simulation time. And then to schedule our events, we have an event queue, and we call it Q. The event queue is just a priority queue, a data structure that allows to store events or store general objects together with a priority, and then retrieve the object with the lowest priority. So in this case, we will use the time as priority, and then we can retrieve the event with the lowest execution time. So to begin our simulation, we have to schedule all events to fill our schedule. And here's what scheduling looks like. If E is a currently possible event, we draw the execution time, in our case from an exponential distribution, and then we requeue this event at this execution time. Requeue is an operation that if the event is currently not in the queue, it just gets added to the queue with this priority, and if it is in the queue, its priority is updated. And if the event E is possible, we will remove it from the queue if it is currently in there. But of course, at the moment we're at this point where we're doing the initial scheduling of events, so there are no events in the queue. So after we've done this, there begins our simulation loop, where we dequeue the next event from our event queue. We get the event itself and the time when it is scheduled to execute. And we execute this event and get a new state, and we set the time to this time we got the event scheduled to. Then we reschedule the event we just executed because it might have to happen again, and it's now no longer in our schedule. And then for each event that is affected by E, we have to reschedule it as well. This part is generally, this finding out which events are affected is generally the difficult part, because in a simple model, you might just look at your model and know which events are affected. In a complex model, there's a lot of room for mistakes here. And so ideally, you want to have a simulation software at hand which helps you with exactly that and does this rescheduling automatically. So ML3, which the language which I've shown you, does this, but it's only a research prototype, and the currently most used tools for agent-based simulations don't do a lot to support this rescheduling for discrete event simulation. You have now seen two ways to advance time in agent-based models. The first is discrete time simulation or time-stepped simulation, where time advances in fixed increments, and all actions and events happen at the same time at these steps. You have learned of some of the problems this might cause, for example, with the ordering of events that happen at the same time step. Then we had a look at a different way to advance time, discrete event simulation, where time jumps directly to the time of the next event. We looked at an example, and you have seen a way to implement a discrete event simulation through scheduling and rescheduling of events in an event queue. Even if you do not use a discrete event simulation in your simulation project, you are still able to be more careful with a discrete time simulation. Be aware of potential problems, handle the order of events carefully. Some ABM tools will help you with that, for example by processing agents in a random order each step by default. And choose the time step carefully. You may vary its size to see if it makes a difference for your results. Thank you for watching. If you have any questions, please do not hesitate to contact me via email.